My name is Aliu Kasimu, and with me is Ahmed Jamiu Okoyemi. So we have Stefan, who is going to do a presentation, and I'm just going to give a very brief introduction of our speaker. So the speaker is Stefan. He's a PhD student in the Nonlinear Structural Dynamics group at the Department of Civil and Environmental Engineering in Hong Kong, University of Science and Technology. He completed his bachelor's degree in civil engineering at HKUST in 2022 and joined our research group and joined this research group that same September, focusing his research on the application of machine learning methods to working dynamics. This is a problem, if you know, that has challenged researchers for over 6 decades, a very long time. So Stefan's work takes a refreshing departure from current machine learning trends. Rather than pursuing black box models that dominate today's field, Stefan focuses on interpretable techniques that allow us to actually see what's happening beneath the surface. His presentation will explore how these interpretable machine learning methods can reveal the causal relationships between earthquake characteristics, structural properties, and system response. Specifically, Stefan examines how features describing seismic waveforms and structural slenderness relate to peak responses and failure outcomes. What makes this approach particularly valuable is its emphasis on understanding over pure prediction accuracy. After more than 60 years of research in working dynamics, we still don't fully grasp all the underlying physics. Stefan's work aims to use simpler and more transparent models, not just to predict outcomes, but to unveil the physical mechanisms that we have long sought to understand. Please join me in welcoming Stefan. So Stefan, you can share your screen.
Okay.
And then, yeah, just do your thing. And
Okay.
feel very free about this. This is not a formal thing. We just want to enjoy science and engineering.
Thank you for the introduction. Let me get this. Okay. So yeah. So my presentation will be on basically presenting some new perspectives on the causal relations between the response of a rocking block, which I'll get into what that is in a minute, and intensity measures via some ensemble machine learning methodologies. And this is a paper that's been published by myself and my colleagues, Dr. Giouvanidis, Dr. Loong, and my supervisor, Professor Dimitrakopoulos. And at some point in time, we've all basically worked at the Hong Kong University of Science and Technology. So it's like one family there. Okay, so let me just go straight into it. So let me give you some context as to why this research is important. So this is as you can see on the left, this is a structure in Greece. It's called the Parthenon. It's extremely old, constructed in the 400 BCs around. And what you can see here, actually, let's see if I can get a pointer. Can you see my mouse? Yes, okay. So actually what you see here, these columns are, well, let's say they're, we can model them as rigid, like rigid bodies, and there's a collection of them here. And what you're seeing here is you have one kind of slab that's resting on top. There's no connection between this top part and the column. And the same thing can be said for the bottom part, this foundation here. So this column is simply resting on top of the ground, you could say. Okay. Now, as we know in modern, innovations in like buildings and etc., we tend to have foundations, we tend to have all these different types of seismic dampeners, etc. But you still have failure in those more modern structures. Okay, when you have an earthquake, for instance, or some sort of seismic event. This structure, the only damage that has been sustained is due to war. Greece itself is a very like seismically active zone, and yet this structure still remains intact till today. So this has piqued the interest of a lot of these engineers trying to understand, what the mechanism behind this is, right? And just to give a little taster, you can see at the bottom left, I've put like this little rocking structure, right? You can see like the faded out is the resting form of this column. And when the ground kind of shakes, you have this tilting action. So as it tilts and it goes back to the equilibrium point, you'll have an impact, which is basically how sorry, which is basically how the structure dissipates energy during an earthquake. Okay, but we know that there are many things that basically define an earthquake. There are many things that also define the structure. There's almost too many things to do that, actually. And at this point in time, we're not exactly sure which of these features we should be looking at, for instance, which is why this is basically what we've been doing for the last 60 years of research. So it kind of starts, well, it didn't exactly start with Hausner, but he has written one of the most important papers on this subject thus far. He basically derived the equation of motion for this rocking rigid block. We assume that it's rigid body motion. Here, he analytically derived the minimum required ground acceleration to overturn this kind of rectangular block structure here. And since then, because what we're dealing with in his work is very basic, like sine pulses, right? So here we can actually analytically derive something. But as we know, with earthquakes, the waveform of the earthquake, the acceleration, is kind of crazy. So when we want to move to more realistic behavior of these structures, we want to obviously use the more realistic version of the waveform. And we haven't had much success until kind of recently, where we have been trying to kind of utilize these input variables, which we'll call dimensionless intensity measures. I'll get back to that in a little bit. Basically, they describe the waveform of the earthquake and also what kind of structure we're playing with. Okay. And using this, we want to kind of predict the peak response of your structure, how much it rotates by, or whether it will fail, whether it'll go kind of fall down on its side, right? We kind of did traditional methods until 2018. And well, AI came about, it became very popular around between this period of time. So a lot of people thought, okay, let's just use some machine learning black box and give it some data from like numerical simulations. We get something out and then done, right? But here's the problem, right? You have a black box problem. You give it some data, it gives you a number or some sort of accuracy, and you have no idea how you've arrived at that, right? You don't know which of these dimensionless intensity measures are the most important. You don't know if there's any interaction between multitude of these input features, right, in predicting your output. How much do each of these contribute to the output, right? Even if they're not that important. So that's kind of what we want to discuss today. So we want to kind of go through I want to find the importance, the relative importance of each of these intensity measures, hence IM here. You can just think of them as input variables. So you have this input variable 1, 2, 3, etc. And you have it's essentially an equation, and it'll give you some predicted angle of rotation of the structure here, right? Then we want to know how do these interact with each other, right? And then finally, kind of can we visualize this interaction if there are any, right? Of course, a byproduct of this is we want a very strong and like a model that can predict, the outcomes of an earthquake, but that's besides the point here. So let me go kind of break down the physical problem that we have. So this is the kind of model we're playing with here. We have one singular block that could be a column or some sort of, I don't know, like a historical art piece in a museum, and you want to kind of study its behavior when it's rocking, right? During an earthquake or something. This is also prevalent in like nuclear engineering. This is primarily how we store kind of our waste. We have these kind of silos we placed down, and we have like the nuclear waste inside, right? So it's extremely important. We want to know how these react when there's some seismic event, because if they overturn, well, now you have nuclear waste out in the open, right? Anyways, so it is known that we have some minimum acceleration, right, of this earthquake, let's say UG double dots. And if you don't, if your earthquake is weak enough and it does not exceed this kind of parameter G, gravitational constant, times tan alpha, alpha here is basically the slenderness. It describes the slenderness of our structure. If it is not greater than this value, then you have no rocking. Okay. This doesn't require machine learning because you can easily tell when your structure will like start moving or not. Okay. Now, if it is larger than this, yes, then we either have rocking overturning, the structure will fail, it'll go on its side, or it'll safely rock. Basically, it'll initiate rocking and kind of after some time go back to static, right? Some equilibrium form. So we have two classes basically, right? We have failure and no failure. So here's our classification problem in the like perspective of machine learning, let's say. On the other hand, right, if we know that the structure will safely rock, we want to know what's the maximum tilt it kind of experiences during this kind of seismic event. Okay. Now, in this kind of system, we're going to assume that there's no sliding or uplift because they, depending on your problem, these also are different types of failures, right? We're going to assume that the structure is heavy enough so you don't kind of have this flight, right? Especially for things like nuclear waste, where we kind of guarantee this by putting a heavy object or slab on top, okay? Anyways, so you have the slenderness angle, as I described earlier. You also have this rocking frequency parameter, but in simple terms, this basically describes the size of your structure. Okay, this R here, this half diagonal length. And then let me go to how like default, well not default, how earthquake, a realistic earthquake can be defined or categorized. Okay. As you can see, I'm just gonna give a little sneak peek there. Like 19, I've only chosen 19 different ways of describing a waveform, but you can have a much larger set of input variables. Okay. What I do want to say that's important is that we have kind of defined or categorized each of these based on certain aspects of the waveform. For instance, when I say intensity-based IMs, they're usually playing around with things like PGA, PGV, PGD, which are the peak ground acceleration, velocity, or displacement. Basically, how intense is my earthquake, right? So that's kind of self-explanatory. We have things like frequency-based, duration-based, integral-based. To be honest, we had to change the name of these variables thanks to reviewers, but originally these basically describe the energy of my excitation, the energy kind of stored in these. And also we have the spectral based IMs here, which are kind of like newer forms or newer ways of describing these kind of earthquakes, even though they don't strictly describe the system we have here. Okay. Because when we say spectral, we're talking, well, here we're talking about like a SDOF oscillator. But anyways, some people think that it's a suitable way of describing the system. So, okay, we go ahead with that. We want to test whether these actually, are these work. Okay. So here, before we actually start using any sort of machine learning, we need to kind of have some framework, right? Some idea of what we want, how we want to use machine learning. Okay. So first we need a data set. So we're going to run some nonlinear dynamic analysis on like this rocking block here, our system. And we have like a very large suite of earthquakes, right, for a given criteria. Then very briefly, we want to perform some post processing. Here, this is like the variance inflation factor analysis. I'll go into what that is. Essentially here, what we're trying to do is find a set of independent variables, okay? Because here we don't know if they're independent statistically, okay? And I'll get into why that's important. Once we have our set of independent variables, we move on to training our model. Up to this point, what we have is a black box model, right? We feed it data, it predicts something, you get some accuracy, but we still don't know like if there are any interactions with these variables or what have you, right? That's what stage 4 kind of aims to do, right? Is the main part of this work. We want to employ something called interpretable machine learning, where we can kind of visualize, right, how or like, yeah, how each of these input features kind of affects the outcome. Outcomes being either whether the structure fails or not, or what's the kind of peak rotation we experience. Okay. Um, so first, what is our data, right? What are we playing with here? Here we use some sort of MATLAB script and we mass produced a lot of results. We have like 100 different ground excitations or earthquakes, okay? And the relatively strong ones, magnitude of 6 or greater, right? Also, we are playing with around 1,000 different unique structures or rigid blocks here, these kind of rectangles. We kind of guarantee them by using something called Latin hypercube sampling. It's basically a method of finding unique combinations of this, how slender your structure is, and also how large your structure is. Okay. So ultimately, we have 10,000 pieces of data. We know that only technically there are 3 classes, right? No rocking, safe rocking, and overturning or failure, right? Only 2 of these are important, so we have to first separate them. And I want to bring your attention to the fact that for the failure cases, this kind of middle histogram, let's call it that, there's only around 4,400 data points we play with here. For the safe rocking, we have 24,000 cases. Okay, so just keep that in mind for a little bit because that will be important later. So now we go to stage 2, and where we employ kind of a variance inflation factor, or VIF for short. Now, what is the purpose of this, right? Earlier, I did mention that we want to find a set of independent variables. Remember, we had 19 different 19 different variables, right? Now we want a set of those that are independent from each other. Why is this important? Well, actually not even depending. Traditionally, when you have some sort of, let me phrase it like this. In machine learning, there are ways of determining the relative importance of input features, right? So in our case, it's the intensity measures, IM1, 2, 3, etc. Now, if you have 2 variables that are correlated, let's say their importance is high, okay? So if I change the value of this, it will most likely determine the outcome of the block failing, for instance, right? Now, 2 of these are highly correlated and they're both important. If I were to give the machine learning model, I don't know, 100 of these kind of different variables, and it identifies one of these 2 variables as important, it will artificially reduce the relative importance of the other important yet dependent variable. So we lose information this way, right? You get the results back and you say, okay, let's say IM1 and 2 are correlated, but both important. Your analysis will come back and it'll say IM1 is very important, IM2 is useless, which is false, right? This is not true. They just happen to be correlated. And the machine learning model doesn't know how to deal with this. That is why we kind of want to get a set of independent variables so we can kind of avoid this entire situation. Now, the way we do this is basically a fancy version of using the correlation matrix. But note that when you use something like correlation analysis, like this is only between 2 variables at a time. Okay. Now, what we want to do is this kind of bottom box here. We are basically seeing a multivariate correlation coefficient here. And then you can kind of identify whether one variable is related to another or not statistically. So you have the score, and this literature, a lot of literature kind of quote this VIF is equal to 10, which basically means if I have, let's maybe go here. If I have a variable that has this threshold above 10, for instance, that means it is correlated with something, one of these variables, right? Now, the reason why it's 10, we can actually backwards calculate what this correlation coefficient is. And that's kind of like, you can play around with it. It doesn't have to be 10. But for our study, we kind of thought 10 was suitable because this is sufficiently low if it's 10. Okay. Anyhow, so the top figure basically is talking about the independent variables for predicting the classification problem. So for predicting failure or failure or safe rocking, okay. And the bottom one is to predict the peak amplitude of rotation. So before I said we had 19 variables to start. Now we have something like 6 for classification, and we have, I think this was 11 for regression. So it's a lot better than what we had before in terms of, I mean, if you're playing around with 100 variables, right, it's almost impossible to kind of interpret anything, right? So it's also a good thing that you cut down the size of what you're looking at, okay? So yeah, let me start with this. So now we go to stage 3, right? So far we have generated our data. We have found the set of independent variables we want to kind of investigate, okay? Now we want to train our machine learning model. And what we decided to go with was a very simple yet traditional model called a random forest. Okay. Essentially, what it's doing is you have a collection of very simplistic models called trees, hence the name random forest. Okay. So the forest is made up of a collection of trees here, as you can see. And how these models pretend the output we're trying to get is classifying failure or no failure. Okay. How it does this is that based on your training data, you give it some input X, right? You have X1, X2, X3, you have these values, right? And this tree one says, okay, is the value of X1 greater than or less than some set value? Let's say 3. If it's yes, it moves this way. If it's no, it goes that way. And the idea of this simplistic model is sorting stuff, right? It's essentially trying to sort out in these little green nodes here, they're called leaves. We're trying to sort all the data into nodes such that if I look at this one, for instance, it'll only contain data that's related to, let's say, failure. And this guy may be to non-failure, right? And the reason why we need to make a lot of these trees is that if I base my prediction based on one model and it's wrong, right, then that's it, right? But what if I had 100 different models like this, these trees? Now you basically have a council, right? You ask tree 1, hey, I have this excitation, right? Or this earthquake, I have this structure. Will my structure fail? Let's say the first guy says yes. The next guy says no, and so on. And basically, you're trying to find the majority vote, right? If enough of these guys say, yes, your structure will fail, that'll be the output that you get here. And that kind of makes it a little robust when it comes to like outliers and things like this, right? Because it doesn't just trust one of these models, right? So that's the kind of the strength and the reason why we chose random forest. We also did kind of test using other traditional models beforehand, like support vector machine, etc., Gaussian process regressors. The random forest did perform the best. But anyways, I just want to kind of explain the inner workings of a random forest. So you can kind of train your model, right? You get some training accuracy, okay? But up to this point, we're not really sold on the whole idea. Why? Because the training accuracy is based on only, here we have 80% of our of our data set. This is training, right? So it's using the ground truth of the data set here, right? The one we simulated to kind of see whether the model got it correct or not. That's how we get accuracy, right? But we want to see how our model performs when we give it data it's never seen before, right? Because that's kind of the whole point of a model. We want to see how it deals with interpolating and extrapolating, right? So then we show the remaining 20%. Now, note this model is trained but has never seen this data before. So now we can do the same process. Now we get some testing accuracy, and this is what we want to look at, right? We want to see, okay, I give you something you've never seen before. How well did you perform, right? So now let's go through some accuracies, or how well did our model perform. This is usually where most papers will stop, by the way. But anyways, so when classifying whether you have failure or so here we say overturning or safe rocking, right? If you're just to look at the accuracy, you get 96%, roughly, prediction-wise. But here we choose to use something called an F1 score, which is basically a harmonic mean of this thing here, precision and recall. And the reason why we're using the F1 score, not accuracy, is accuracy does not account for the imbalance of data. Now, if I bring you back all the way here, we only have 4,400 cases of overturning, right? And we have 24,000 cases of safe rocking, which means that the model only really has to predict the safe rocking cases, the majority of these. It could get all of these wrong, right? But still, 24,000 correct versus 4,400 wrong, that's still pretty good, right? But that's not the point of this kind of prediction. We will also want to see how well it performs when we want to kind of predict overturning. Failure is the most critical case in our system, right? So that is why we use the F1 score here, which kind of helps alleviate this problem, basically. Regardless, we still get around 88% accuracy or F1 score. So it's still better than anything we've seen in literature, okay, so far. The same can be said for regression. Here we get where is it? Yeah, get a R squared of 0.84, which is quite high. Currently, the models we have using machine learning is 0.77. Traditional methods, we get something as low as 0.5. So basically, it's like flipping a coin at that point. So anyways, we have a model that's capable of predicting whether your structure fails or not. It also can help you predict the peak rotation. That's what the regression is. Okay, that's nice, right? But as I said earlier, we want to find out how much each of these input variables contribute towards some said prediction, right? Is there any interaction between two or more IMs or these input features? When I mean interaction, I mean like if I increase the value of, let's say, IM1, right? And let's say nothing much happens to the outcome of the structure, okay? If I increase IM2, nothing happens to the structure. But if I increase both, for instance, there is a chance that the outcome of the structure will change drastically because there is some sort of interplay between these two variables, right? And it's not just like it's not as simple as saying I increase one and the other and I have like a drastic change. What range of values of each of these IMs will I have kind of this interaction, right? Because these IMs have physical values, right? 30, 50, 100, something like this. So where does this occur even? So today I'm just going to explain one of the methods we used, which is the Shapley additive explanations or Shapley analysis. The other one we used is partial dependence plots, but I believe Shapley value analysis was the one that, well, at least in my opinion, it kind of highlights the overall power of like interpretable machine learning here. And you'll see it why in a minute. So here, essentially what this is trying to do Originally, I believe this is from game theory, originated from game theory. But essentially what it's trying to do is trying to find the marginal contribution of one of these items when trying to predict something. So here, I've kind of showed an example. If we have the complete model that has all the items we have, right, it gives you prediction y hat, for instance, right? Now I say, what if I only realistically use one of these variables, right? Well, I'll get another prediction. What if I get this guy and only these two? I'll get another prediction. What if I have the first and the third one? And you can have an insane number of combinations, right, of these. And what you'll end up getting is the marginal contribution of the common guy that remains. Let's say I am one here, right? And you can do this for all the variables, right? And you will essentially get the kind of how much does one of these variables contribute when predicting something, okay? So we end up with a figure like this. Now on the left, if you've never seen this before, it might be a bit confusing to read. Um, so I want to bring your attention to this color bar first. So the IM value is like the physical value of the variable. For instance, if the range of IM1, for instance, is 0 to 50, right? Then 50 will be high, 0 will be low. Okay, that's what the color kind of shows. So these are relative, right? Now here, what we have on the left, I've kind of put all the variables that we were investigating, right? For instance, this is for classification. We only had 6 variables. And basically, if we take the absolute value of this kind of range here, the spread determines the importance of the variable. And here what I've done is I've kind of ordered it in terms of the most important to the least important. Okay. Also for this Shapley value, is these basically shows kind of like the contribution towards a certain class, right? So on the right here, we have overturning, failure of your structure. If we go in the opposite direction, this is a contribution towards safe rocking. Okay. So for instance, for the first guy, we can see that for low values of PGV, the peak ground velocity of my excitation, I'm more likely to have safe rocking, which makes sense. The less intensity of the earthquake, then, less chance of failure, right? Or more chance it'll basically initiate rocking, but then go back to equilibrium. Okay. Um, and then here we went a step further. So on the right here, what you can see is I have one model that only has the most important input variable. Okay. And by itself, it gets a F1 score of 58.6%. Okay. Now, what if I have 2 of the most important IMs together? 3, 4, 5, etc., right? Until you get the full model. The purpose of doing this is that I want to know exactly how many of these IMs do I realistically need, okay, to describe the entire system. And once I get this, now I have narrowed down from 19 different variables I could realistically look at to something like 3, right? Where I can now do some other things to it, like later, to kind of really understand the system from a physical perspective, right? Study the physics of the problem. We don't have to kind of look at these 19 variables and kind of wonder, okay, how am I going to tackle this problem? Now we only need 3, for instance, right? As you can see here, 3 already gets like 85%. Everything else is just like minimal, right? Improvement. And we do the same thing for the regression. Also note that here we're not going to simply say, okay, this variable is the most important, this guy's the least important, and that's that, right? Here we also compared it to kind of what we have discovered in prior literature, right? From the physics of the actual problem, right? And there's a very good agreement between prior literature and kind of which variables we found were important or not important, which is good. I mean, it's a good sign, right? There's some sort of there's an agreement between what we have from theory or like experimental data and what we have from machine learning, right? Essentially, what we're kind of showing here is that we haven't taught this machine learning model any physics. We just gave it data, and yet it can still understand which of these variables are important without really understanding the physics, right? That is important to us. Now, here is where we kind of go into the how we kind of show the relation, like the interaction between variables. This is kind of where we understand the causal relationship between input variable and output variable, right? Here, what we had was okay, low values equals let's use this one. Low values means safe rocking, higher values means rocking overturning. Let's say for the first variable, right? But here, I can actually get exact, well, not exact, but rough values of like what we mean, how we achieve these plots, okay? And at the same time, I'm not only showing you like the contribution of one of these variables. If we look at the color bar here, this is another input variable. Essentially, what I'm saying is if I were to hold, let's say, if I were to hold this range from 0.4 to 1.5 for the first variable, okay, you can kind of see there's a little branch here, right? There are two branches. So you can have the exact same intensity earthquake, right, from this range, and yet you'll get two very different outcomes, right? So here, the y-axis, I should have actually mentioned, the y-axis here is the contribution of one of the variables towards, let's say, overturning, failure of the system, or safe rocking, right? This means that if for the same intensity earthquake, if the period of my earthquake is higher, right, then I have a huge kind of jump in probability of having rocking overturning. And if it's a lot lower, then I have a considerably lower chance of having this overturning region, right? And we've done this for all combinations of these variables. Obviously, I'm not going to present all of them here, but essentially, what we can identify are these ranges where you have these branches or this spread here, right? Now, what we have on the right, this kind of, oh, sorry, this green and red figure here, is now that we have identified certain ranges where either you have safe rocking, green, right? So 0 to 0.4 for the first guy, for instance, failure of the system, overturning from 0.4 onwards. But now we have this hashed kind of region here where we know that there's an interactive kind of part, right? If I just simply increase this guy, it doesn't necessarily always mean you have overturning, right? It depends on the values of a different variable. And that's why we have this hashed kind of interactive range. So now if we were to kind of do some traditional methods like fragility curve analysis, etc., on this kind of the physical problem, we know what we're looking for now. First, we know what variables we want to look at. And number two, we know what ranges we want to look at. And we have an understanding that there will be an interactive kind of effect here when predicting failure of the system or no failure. Same can be done for the regression here. But basically what we are trying to show is that we have successfully kind of started with just a problem with a lot of variables, well, comparatively not a lot of variables, but still a sizable number of input variables. We reduce the number we're looking at. We've arrived at a black box model that was very good at predicting things. And now we're trying to understand how the machine learning model works, right? Now, the reason why we're doing this in the first place is that machine learning excels at identifying patterns, right? That's one of the big strengths of machine learning, right? And if traditional methods cannot do this, and machine learning can, and it still coincides with what we understand from the theory, right, of the physics of the problem, we want to know how it works, right? How the brain of this model works. That's essentially what we've achieved here, right? But yeah, that's basically the conclusion of my presentation. If you're curious, because I kind of briefly glossed over some details, but the full article is here. You can take a look at that. And also there's some recent publications from our research group that also tackle kind of the same topic, stuff like that. Okay. Thank you very much.
Great. Stefan, thank you so much for such a really, really nice presentation. And I like that you did not assume that we knew. You just took everything slowly, which is really, really great. Ahmed, do you want to start? If you have any questions? Yeah, and please, this session should be very interactive. Okay, just interact.
Yeah, thank you, Stefan, for the nice, very informative for me presentation. Yeah, let me go with in slide 19, or is it 20? Like,
Okay.
aside you talk about the importance of like how the model, or discovery of the importance of variables.
Yes.
Yeah, the variables. So like I'm just curious, like, is there a possibility of deriving a relationship, could be linear or non-linear, instead of just maybe like I'm trying to figure out or wrap my head around the importance. Like, I feel like importance still deals with maybe pattern. So I'm trying to, like, is there a possibility of maybe leading to probably analytical relationship also?
Yes, that is actually that we've done some brief work on that, not published yet, but basically once we identified, let's say for this problem here, so here we essentially have, here we went with three variables. We kind of plotted the cluster of data points, right, for these types of variables, and we did kind of identify this kind of barrier, okay, in the graph that separated the safe kind of rocking cases and the overturning failure cases. When this barrier, right, in 3 dimensions basically forms, as you said, it's not an analytical solution, but still it's a linear or nonlinear form, right, using these three variables that can still predict whether your system will fail or not. And that has great value, right? Once you can establish this. So yes.
Yeah, and really towing this line of thought that Ahmed just explored. I think this is like one of the, if you think about it, one of the cases where, okay, I know what I'm looking for. I know that this is important, this is not important. And maybe I don't even need to derive from first principle. Just write something that makes sense and test whether it follows the curve. I don't know, I'm just thinking. Because for example, if I know, like if I know, for example, that I have some sort of maybe a curve, then maybe I know that, for example, I should have an x squared or x power 3, something like that, or some e exponent, some exponent, and then combine a few things and perhaps bring out an empirical relationship that's it's empirical in that it doesn't really stem from somewhere. It just it just works.
Yeah, exactly.
But I want to ask, you want to respond to that before I ask?
No, you can go.
Yeah, you can go.
Okay. So now that we know, because let's go back to why exactly are we doing this? So I have a structure, okay, and then earthquake happens.
Yep.
Okay, and the structure is either safe or not safe. Okay, now we know that, okay, so when we write the free body diagram, or we try to analyze the mechanical model of such structures, we know now that, okay, this is important and this is some features are important and some features are not important, okay?
Yep.
Now that we know, what's next? This is the first question. What's next in terms of the actual structure? How can these predictions help in maybe safety or, okay, in analysis, yes, but analysis will be after the damage has been done, right?
Yeah, exactly.
Yeah, so this is first question. The second question is, in obtaining the response of these of this system, the response is the intensity measures. The response of the system using simulation. I can see there's a human hand in this, right? Because you define basically that, okay, this is the response I need. What if there are other responses that are key that we did not know of, so we did not use it to train the model?
Okay, so for the first one, right? The immediate kind of direction we would want to take is, let's say, for control systems, for instance, right? I know in the grand scheme of things is not that important, but kind of how this problem came about originally was kind of the protection or the preservation of, let's say, historical pieces of, structures or even artwork, like a ancient vase or something, right? Something like that. Now, if we want to kind of introduce a control system that prevents the system from either achieving too much rotation, such that there's might sustain damage or even failure, right? Overturning. Now we have variables because we know essentially here tan alpha, right, is related to the structure. It's related to the slenderness of my structure. And we know that we can measure this before anytime we want, right? It doesn't have to be after the fact. Now the important part is this peak ground velocity. This we don't know before the earthquake, right? This is something you'll only know after you experience the earthquake. This is why now we have a range, right? We know there's a particular range in which, okay, now it's getting a bit dangerous for this type of structure, right? You're approaching this overturning kind of region. That's when maybe you can introduce a control system that will prevent, like, have something that, counteracts the motion, right? So prevents achieving this kind of critical threshold, right? That's kind of idea number one for that kind of stuff. Because realistically speaking, if we're to think about this from, from studying this, actually, you don't actually need a control system. What you do need is a huge structure. If your structure is large enough, it'll never overturn. Right. But of course, you cannot achieve this realistically, right? It's not like you can have an infinitely large, like a radioactive silo, for instance. That doesn't make sense. That's why I think we need to use these kind of control systems. Now, whether you can predict the evolution of things like the ground acceleration or velocity during the earthquake, that's a different problem, right? That's a completely different problem, but that's something that now that we know that these variables are important, we will try to develop methods that can do that, right? At least now we know what we're looking for, basically, right? For the second question, I actually didn't fully understand. So the intensity measures, the IMs, let me go back to the table here. Yeah, so any of these. So these are my inputs, right, of my model. So let's say,
so the question, maybe to rephrase it, is what if these IMs are not exhaustive?
Exactly, yeah. That, to be fair, that we're not sure about, right? Because as I said, how we've selected these intensity measures, basically the most popular ones that we've kind of found in literature, right? The ones that have been extensively studied, yet with no avail, right? Using traditional methods. And we have also included some of the more, how would I say it, the newer intensity measures that have gained more traction over the years, right? but we also still want to test whether these, are,
Yeah.
important or not. But of course, they could be like an IM20 we don't know about, right?
Yeah.
Um,
I
but
understand.
yeah, but
Okay.
I mean, there's also the good thing that we've kind of categorized these, right? So if we know that one of the intensity measures is important, right? There might be an intensity measure that's correlated with a new or an intensity measure we have not looked at yet. Then we can take that one and then see how it performs, right? Maybe it has a better performance. And when you have a better performance, then we can kind of pick the brain of the machine learning model and see how it how it utilized this variable, right? And then we can derive the same plots.
And then can you go back to the IMs?
Yes.
Okay. So
I think I held the
that's
arrow
fine.
key way too long and it just okay. Back to the IMs.
Yeah. So for Ahmed and everyone, maybe we should finish this in exactly 1 hour, so maybe 10 minutes from now.
Okay.
So that we don't take too much time
All
from Stefan. Stefan, again, thank you so much.
Oh,
Okay.
no problem. It's an
So
honor.
my question is, the slenderness ratio, is it it's dimensionless, right?
Yes, all
Is
these
PGA?
are
That's
yeah.
the question. Is PGA is in terms of acceleration units?
Yes, that's
PGA.
correct.
Okay, so the IMs are dimensionless. What about P?
P is also
A ratio is unitless, right?
no,
Is it?
P is not unitless. P
Okay.
is
So some are not dimensionless.
yeah, exactly. But
Okay.
the entirety of this IM is dimensionless. That's why I've kind of constructed it in this way. If that makes sense.
Can you explain what you mean by the
entirety?
entirety?
So basically the ratio of the numerator and denominator makes it such that this IM2 is dimensionless and etc. But things like P or PGV, they're not. They are dimensional. They have
No,
units.
what I mean is if alpha is dimensionless,
Yeah.
the only thing we have in the numerator is you have ms to the -2, right?
Yeah.
For G.
Essentially, yeah.
So
Essentially,
in the numerator, I'm looking for ms to the -2 also.
yeah, same.
So
Because
if
you
you
have
say P is not okay. PGV. What's the units for PGV?
meters per second is a velocity.
Okay. So P is per s.
Yes.
Okay.
Correct.
Okay. And then I was also wondering, maybe Ahmad, you want to ask a question? Let me not ask. I want us to.
Yeah.
Go ahead. Sorry.
Regarding like I'm just curious about when you were downgrading or simplifying variables, like it still leads to equation I was raised earlier. Like I don't know, like considering uncertainty of maybe not just earthquake, maybe other scenarios whereby we have extremely uncertain conditions or variables.
Yeah.
Like I'm just curious, how were you able to simplify to a certain or discrete number for you to use as
yeah.
a feature in your model? Yeah.
Yeah. I mean the kind of the reason why we have I guess we've essentially simplified it to kind of labeling, let's say this earthquake can be partially described by the peak ground acceleration. For instance, right? You're associating this waveform with one number, right? We can agree on this. But the reason why we are doing this is that these variables, let's say the peak ground acceleration, is associated with fragility curve, and you can basically, given like a type of earthquake, you can actually kind of predict the likelihood of achieving this ground acceleration, for instance. So some of these variables can be kind of predicted beforehand, if that makes sense. Not predicted in the sense that you know exactly what the number is. You know the probability that you'll have this kind of the structural encounter this peak ground acceleration, for instance, right? And that is valuable from like a design perspective. right? Because then you can design for, let's say, some, I don't know, control system or something, or a structure that, okay, I expect it to encounter like a waveform that has this peak ground acceleration. And the probability of it achieving this peak ground acceleration is some number, right? So we're associating kind of these values to a probability of this kind of earthquake occurring, right? Because otherwise it's almost impossible to do anything, right? Because for, let's say, a mathematical waveform, that's like a sine pulse, you know exactly how it is, right? You can exactly define it. But for an excitation like this is impossible, right? That's why we've unfortunately resorted to the use of these labels, right? Things like PGA, things like this.
Can I ask? So I was wondering, you had during your data generation stage, you had a bunch of variables, right?
Yes.
And then at the end, they like narrowed down to fewer variables.
Yeah.
So I was wondering why this down sampling of the it's I would think, okay, and please explain, tell me if I'm wrong. I would think that this down sampling of the features or reduction number of features will come after you do the sharp analysis. Because now I have 20, for example, I have 20 features. I do my sharp analysis. That's like a feature importance analysis.
Yeah.
And then I know which is important, and then I remove those that are not important.
Yeah, but that is where you run into this problem here, right? So if I were to skip this process of finding the kind of, because what we do first is not based on the importance of the variable, right?
It's correlation first.
Exactly, correlation first. So if we were to skip this, right, basically, the Shapley analysis will attempt to equally distribute the contribution of predicting something, right? Let's say failure, to these two different variables, right? It'll attempt to, but in reality, what will happen is that it'll identify one of them. Let's say IM1 and IM2 are correlated, right? But are both important by that logic. As in, let's say IM1 is important, therefore IM2 is, right? Because they're correlated. That means that it'll say, okay, well, I can't say they're both equally as important. What it does instead is it artificially chooses, let's say, IM1 and says, oh, this guy's very important, right? And then IM2 will be reduced artificially to kind of fit this narrative. Now this, you lose information now, right? Now whether we keep IM1 or IM2 in this process, that's a different story, right?
Yeah, so what I'm thinking is whether we do correlation analysis before sharp or we do sharp before correlation, I think we still lose information. Why? Why do I say this? Because the threshold, okay, first, was this threshold empirical? So, okay, well, whatever the threshold is, whether it is 10 or 9 or 5 or 20, we're still removing some features, right?
Yes, of course.
We're still going to remove some features, which somehow they add significant, depending on how you look at it. They add to the robustness of the model. Somehow they add. So and if they add, we know statistically that it means they have some new information to add to the model. If they did not have it, will be redundant.
Yeah, of course.
Okay, so either way, whether we do sharp first, correlation second, or vice versa, we're still losing information.
Of course.
We have to lose information because engineering really is not about getting 100%. It's about getting good enough.
Yeah, exactly.
Okay, so maybe it's a good exercise if you have time to check
to
that. Because I've seen this paper. They tried to predict they tried to predict roughness, if I remember correctly.
Yeah,
And
sure
then
did.
this was really the workflow. They got a lot of data, did sharp analysis, feature importance analysis, removed a lot of the variables they thought were useful. Okay. And then based on the reduced feature space, they did the machine learning model and it actually worked, at least from the paper. And I can share this paper with you.
I mean, when you mean worked, what do you mean by that? Like, it should.
I mean, the values, the reduced feature space
Yeah,
was enough for very high accuracy of the model.
I
They
think
use
that's
sharp to
that
reduce the feature space.
that.
You see what I'm saying?
Yeah, I see what you're saying.
Yeah. Maybe it's good something to think about more.
Okay. Yeah.
Yeah. Ahmed, do you have a last question?
Yeah. I
Go ahead.
don't know.
Go ahead.
Yeah. Go.
Yeah, nothing more to say. Yeah.
Okay.
It's already 10
Let me
o'clock
see if
already.
I have another. I really love that your features are dimensionless. Really.
Yes.
Yeah.
That's the
Makes a lot of
important part.
sense. Makes a lot of sense. And instead of using just one variable, you're using a variable that represents a group.
Yes.
A dimensionless group, which is excellent, really.
Yeah.
And I wish more and more of machine learning will be like this. The future should be dimensionless, right?
Yeah.
So that you remove the scaling issue.
Yeah. Exactly.
Yeah.
But, I don't know, like.
Yeah, I think I was going to ask you about the VIF threshold.
Yeah. Oh, there's this 10. Like, why is it 10?
The 10 was it empirical? So you tried and saw that 10 is good.
Kind of. This is basically we've basically saw a lot of studies that kind of deal with very similar problems to what we're dealing with here. A lot of them arrived at VIF is equal to 10, right?
Oh, okay.
Now, like, I'm not saying that we blindly follow this value, right? But the kind of correlation coefficient that you derive from this value 10 is acceptable in this sense. You can make it a lot more stricter, right? You can make it 5, for instance. Of course, then you would lose some of the variables. Let's say PGV will instantly get cut, is literally at the border, right? For the classification problem. So that part is quite tricky, I think. That part's quite tricky. Because if it's too low, then we would have lost one of our most important variables. Now here, the reason why this is kind of cheating in a sense. The reason why we kept it at 10, and once we saw this figure, we were like, okay, we're keeping it at 10. We're not going to reduce it to 5, for instance, right? Is that I know you've done work on non-smooth dynamics, so you know this. This problem here is basically is a game of velocity, right? The transfer impacts and Newton's impact model. This is basically all to do with velocity. We know that it's an important variable. We know it's an important variable. So we obviously don't want to have it end up being cut, right? So we tried the kind of general, let me say standard in quotations, value for VIF. We saw this and we said, okay, we don't have to be more strict than this. Because if we do, we lose this guy. And we know this is quite an important variable, just from the physics of it. So it does require, there's a bit of like caution, right? It does require some engineering kind of judgment, in a sense.
And
You can't
excellent.
just,
And really, this is what I think many papers in machine learning lack.
Yes,
there's no this control, upper and lower limit, because we know that this is, of course we know, right? Because restitution, right? It will bounce, and the only reason why it will go up and down is because of energy, the interplay, potential, kinetic, and so on and so forth. So we know that it is important. Okay, and this is why this work, I think, really stands out. That we are doing it as engineers.
Yeah.
We know we know the threshold, to accept and what not to accept. So really, this is. I think I don't have any more questions. Ahmed, to check again with you if you have.
It's good from my side.
All right.
Thank you so
Thank you
much.
very much again, Stefan. Ahmad, you want to
Yeah.
close the session for us since I opened it?
Thank you, Stefan. Thank you for this. We hope to have you more, have you
Yeah.
present more of your work. Yeah, this is really
And
informative.
we'll be monitoring your Google Scholar account. Once we see the next paper,
Yes.
we'll invite you again.
Yes, thank you. Thank you.
Yeah.
Thank you. Thank you
Yeah,
very
thank
much.
you.
Thank you.
I mean,
Okay, bye-bye.
yeah,
Okay,
bye-bye.
go ahead.
Oh no, I was
You want to say
just yeah.
something?
Yeah, I was just gonna
Sure.
say
Sure.
no, like is actually I really wanted to kind of present here. I know that
Thank
I've been
you.
kind of elusive in that sense that I was always busy and then didn't have time. I mean,
I know.
the
Yeah, I
schedule in
know.
our group is a bit crazy these
Yeah,
days.
it is.
But yeah, I'm glad that I can finally, present my
Yeah.
work. Yeah.
Thank you. Thank you so
Thank
much,
you so
Stefan.
much.
Thank you.
Thank you.
Thank you.
Really
Okay.
appreciate it.
Bye-bye.
Good night, everyone. Bye-bye.